Alright, so this is a tutorial for the AC node equations tutorial in Circuit Tutor. I'm going to do a mastery level problem in hopes that this will address any concerns from any previous levels. So the first thing we have to do is pick the ground. I'm going to pick the node with the most voltage supplies. This will just make our life easier later, but you are free to pick whichever node you prefer. It doesn't make a difference in the solution. So the first thing we do is voltage constraints. I'm going to start with the V1S voltage supply. On the positive end we have V6 and on the negative end we have the ground. So we can define V6 minus 0, which is just V6, as the definition of V1S, which is given underneath the circuit diagram. So we check this equation, it's great. Now we look for other voltage supplies. It looks like we have V2S. So as we did before, on the positive end we have V4, negative end we have V6. So that would mean that the difference between V4 and V6 is the definition of V2S. And you can see this being input up on the top. To bring these equations down, I find just clicking them in the order that I want is the best, and then tabbing through each of the input elements. So we have a third voltage supply and it's current dependent. But that doesn't matter. We can still say that on the positive end we have V2 minus 0 on the negative end is equal to the definition provided for it. So V2 is 4 ohms times IX. Check this equation and it checks out. So we have no more voltage supplies. We do have a current supply, but that is not applicable to voltage constraint equations. So we move on from voltage constraints and we move to our KCL equations. So I like to move in the order that the meshes are labeled. If you start with V1, you can see that there are two impedances on it. The first and the second both have a voltage drop across both of them. So we're going to pick terms where we can subtract voltages. And because we're analyzing node 1, we can assume that node 1 is positive, and then we're going to subtract the opposite and then put it over the impedance that it is across. So node 1 worked out. We're going to move on to node 2. We see that there's a voltage supply on that. This would indicate a supernode, but then we again see that there's still a voltage supply. This is becoming cumbersome, so we're going to move on in hopes that we don't need to use that. So moving on to node 3, we can see same situation as node 1. 2 voltage drops over 2 impedances is equal to 0. And we can again assume that node 3 is positive because it's the one we're analyzing. This is because we're assuming that current is moving out. And we input both of these values, check the equation, it checks out. Great. So from V3 we move to V4. We see that there is a voltage supply on here, but that immediately solves our problem, so a supernode of V4 and V5 won't be too ridiculous at all. So we see that in this supernode there are 2 impedances, both with voltage drops and a current supply, and this is equal to 0. So for the first impedance, we're going to say that V4 minus the voltage across from it, V2, over the J5 impedance. Now, again, as we mentioned earlier, we assume that current flows out. So this current is flowing in, which means that we need to have a negative coefficient in front of it. Then for the final impedance, this is again normal procedure. We say that V5 is our start, and then the current moves to V7 over the J9 impedance. And this equation is accepted. So now we check 6. We remember that that's part of the ridiculous node. So we move on to node 7. And this is 2 impedances. The first has the ground on the opposite side. So we only need 1 voltage variable on the numerator. The second one, again, has V5 on the other side. So that can be the difference of voltage term. And the sum of those should be equal to 0. So for the first one, we'll have positive V7, because it would say V7 minus 0, over the impedance for that element, and then V7 minus V5 over the impedance for that element. So now we know that we've had 7 nodes, and it looks like we have 1, 2, 3, 4, 5, 6, 7 equations. This means that we are done Now the only unknown that we're missing is our dependent control source. So we can write an equation for that, which is Ix, and Ix is shown as moving through the 1 ohm resistor. Now, how do we explain this current? Well, current is defined as V over R, and we can see that Ix is moving from top to bottom. We know that current enters the positive end and exits the negative end. So if it's entering in the top and exiting in the bottom, then we know that V3 is positive and V1 is negative. And of course, we have to divide by the resistance, and this will yield the current running through this branch, which is also given by Ix. So we say that V3 minus V1 over 1 ohm is equal to Ix. And now we have every unknown in our system accounted for. So we have to write an equation now for the output voltage, which is given as the voltage across the current supply. So the positive end is given by V4, the negative is given by the ground. So V4 minus 0 can just be written as V4. And we have every equation that we could need to give the output voltage. So no, we don't need to see a solution. And good luck.